Hello everyone, welcome back to the part 2, lecture 12, divergence of a vector field. What is a divergence? Divergence is basically telling you how much flux coming out of a closed surface in per unit area. So what does it mean? So if it's a divergence of E over here, it's electric field, right? So divergence of E is, del operator, we have talked about the last time, same del operator. If you dot product with E, you get a scalar, right? So divergence of E will give you a scalar vector. That vector is says divergence of E, where you like say divergence of E, right, is at point, at a point as the net outward flux in this case electric flux per unit volume. So it's the measurement, right? How much flux coming out of a closed surface? Again, it's closed from a closed surface. From a closed surface. So if you close surface, how much flux coming out of the per unit volume at a point is the divergence. And if you try to find the 12 flux, you have to get you need to do surface integration of that E of the E over the surface to get the 12 flux, right? Or you can also, this is also per unit volume, right? You can do the volume integration of that one here. Volume integration of that one, that's also give you the 12 flux, right? Look at here. So 12 flux can be found. This is the per unit volume, right? So you can do the volume integration over it, divergence of E, volume integration with the 12 flux. Or if you know the flux, then if you do surface integration, which is a closed loop, closed surface integration of that, also get 12 flux. That means these two are equal. That is called divergence theorem. So divergence theorem is telling that your divergence of E, which is net outward flux from a closed surface per unit volume, if you do volume integration of that, you get the 12 flux. Or if you know the flux, if you do the surface integration of that, also get the 12 flux. So this is your divergence theorem. That means you can do either surface integration or you can do volume integration, but one condition is this closed surface. It's a closed surface. That's the only restriction here is a closed surface. And we're gonna try to solve this problem in the class and try to find divergence in both for Cartesian and also spherical coordinate. If you have your book, last page of the book has the gradient, divergence, and Stokes theorem, Laplacian, all of them in the last page of the book. So what is a curl? Curl is a so curl of vector B. So curl of vector B is a cross product. Curl of vector B is a cross product. What it means? It means that circulation or circulation density, be precise, density of V per unit area, right? So if you know circulation density of a vector per unit area, if you do now area integration of that bed, you will get the total circulation of the vector in that area, right? So it's a curl of B is the curl of B is the circulation density of a V per unit area. So then if you want to find the total area, you can do the surface integration for that, and you will find the same thing. But one thing is that your Stokes theorem, also there's another theorem here, Stokes theorem, it can relate your surface integration with the closed loop line integration. What it means, so let's say that you have a ball here, right? So this is your open surface here. This is the open surface, open area. So now you pour water here, right? So amount of water coming from that open area, also the amount of water coming out of the surface. So that means your surface integration could be equal to your closed loop line integration. This is the closed loop line integration right here. This is the this integration right here and this integration right here. So that's your Stokes theorem. Stokes theorem equate your surface integration to the line integration, closed loop line integration. This is only for open surface. We're going to do a couple problem in the class, how to apply Stokes theorem, and also as well as also the gradient and the divergence theorem. We're going to do some problem in the class. And I'll also show you some simulation in the class, how it works. And what is the Laplacian? Laplacian, you remember that gradient of V, right? So if you take if you have a gradient of V, then if you have a dot product with that del factor, that is called Laplacian of a scalar field. This is the Laplacian of a scalar field. What it means, the Laplacian of represents the flux density of the gradient flow of a function. So if you have a gradient of t, if you take the Laplacian of that, that is showing you that flux density of the gradient flow of a function. That's the Laplacian. And that's the application of this in a CT scanner, because you have a 3D image, then you transfer the 2D image. That all happens with the vector calculus. I'm going to do this problem in the class, or maybe a couple more. So your job is to review this lecture before you come to the class, then we'll apply this divergence theorem and Stokes theorem, gradient theorem in the class to solve some problem. All right, that's all for chapter 3. We're going to get to the chapter 6 in the next class.